everyone. So in this video we'll discuss the derivation for the closed form formula of b0 and b1, basically the coefficients of univariate linear regression model. Okay, so this is a univariate linear regression. There is only one independent variable, that is x, and there is a dependent variable y. Now I have used xi and yi. Basically there are n points, the sample size is n. Okay, and for every point there will be a prediction. So yi is the actual value and yi hat is the predicted value, right? So now the difference between them is the error, and you square that error to nullify any negative errors and also to make it easily differentiable, as we'll see in the upcoming part in the video. So that is the square of error, you can say, that is square of one particular error for one particular I, and then you do that for all possible i's. Well, I ranges from 1 to n, and then you take the sum of all those errors. So what you get is SSE, which is sum of squared errors. Sum of squared errors. Okay, so this is sum of squared errors. Now here in place of yi hat, you can substitute this particular value, the model that we have. Okay, what does it mean? Our model simply means that it is a line, right? Y is equal to mx plus c. So you can say that it's like b1 is m, or the slope, and b0 is the intercept, y intercept, or c, if I compare it to the classical equation of a line, right? So b1 is the slope and b0 is the intercept. Okay, so now basically SSE, the sum of squared errors, is a function of b0 and b1, and we have to minimize the error. We have to minimize the error. Error is bad, right? We don't want error, so we have to minimize the error. So error or loss has to be minimized. So that is our aim, that is our goal, to minimize the error. Hence we also call it as objective function. Objective function. And there is a general notation for objective function, that is j, and the parameters of the function are called as theta. Okay, so in this case our j theta corresponds to sum of squared errors. Now what are the parameters of sum of squared errors? Here if you can see, if we focus on this particular equation, if we focus over here, yi and xi is the fixed data set, right? X and x comma y, this is the data set that you will be given, right? You will be given x comma y points. So xi comma yi will be fixed given data set. Okay, now if you can see this line, okay, this particular line is drawn like this. So it has a slope of b1 and it has a y-intercept of b0 or b0. Okay, if I change the slope, okay, right now the line is like this. So as you can see, I have shown you the errors over here. So these are the errors that you can see with the curly brackets. Can you see? So for example, for this particular point, the point on the line, the pink point on the line, that is, this line is the model, right? So the pink point is the predicted value of y. This is okay. So these are all, I will use a separate color for this. Okay, so let's say these are the predicted. So this is, let's say, y1 hat. Okay, and this is the blue point is our data set. So this is y1. Okay, so y1 and y1 hat. Now similarly, the point on the line is the prediction. So this pink or red point, this is y2 hat, and this is the actual data point, which is y2. Similarly over here there is a pink point. So this is the y3 hat. Of course I'm assuming here correspondingly we have x1, x2 and x3. Okay, and this is the blue point is the actual y3. Okay, so there is a gap, there is a difference between, so this difference is the error. So this is, let's say this is e1, this is e2 and this is e3. This is the error, right? And if I change this line, so let's say now I change this line to something else, let's say something drastically different, right? I change this line to something like this. Okay, it's obvious that the error values will change. So basically the error is a function of b0 and b1. As the b0 changes and b1 changes, the error will also change, right? So SSE is a function of b0 and b1. This is clear? I will just erase this line. So SSE is a function of b0 and b1. So this is our objective function. And what is our objective over here? We have to minimize. We want to minimize the objective function because it is bad. Okay. So how do you minimize? How do you find the minima? So if you have studied calculus in your school days, basically you set, okay, how do you find the minima for a particular function? You basically find the first derivative. You find the first derivative and you set it equal to 0. Now because there are multiple variables over here, there is b0 and b1, there are multiple variables, so we'll have to use partial derivatives. So this is the partial derivative of sum of squared errors, that is the objective function, with respect to the parameter b0. Okay, dou SSE, I am calling this symbol as dou. Okay, so dou SSE divided by dou b0 is equal to dou by dou b0 of the SSE function that we have over here. We take the SSE function from here, we find its derivative. Okay, similarly we will have to find a derivative with respect to b1 and set it equal to 0. So in general the procedure is, you can say that dou by dou theta of j theta, you set it equal to 0 and you solve this. You solve this to find the points where the function will have its minimum value, and those values of theta, okay, and the values of theta, so basically you can say that solve for theta, the values of theta for which this particular thing gets satisfied, okay, for which this gets satisfied, those values of theta are the one which we'll use in the model, right? So in this case we'll form two equations. One will be the partial derivative with respect to b0 and another will be the partial derivative with respect to b1, and then we'll get two equations. So now let's just solve it a bit. Okay, so now, okay, so this is the equation that we have. This is the equation. Okay, basically we are using chain rule over here. Summation will automatically come out of the derivative, so that is not an issue. So summation is outside, and then inside this now we are using chain rule. So firstly, coming inside, coming from here, we see that this is a square of something, so it will be 2 multiplied by that thing. Then you go inside. Now when you are differentiating with respect to b0, yi and b1 and xi, all of them are going to be constants. So the only term that will cause or which can be differentiated, which is the variable, is this particular term. The coefficient is -1, so there will be a -1 multiplied by the 2 because of the square sign, so -2 into this. So this will be the derivative of the sum of squared errors with respect to b0. Now the derivative of sum of squared errors with respect to b1 will be, again, you can take the summation out and then you apply the chain rule. So firstly you see there is a square of something, so twice of that thing. Okay, and then going inside you see that the only term which will have a derivative is this particular term, and here you can see that b1 is the variable, right, and the coefficient is minus xi. So the derivative is twice of something, and inside you can see the coefficient of b1 is minus x1, so minus xi, so minus xi. Okay, and finally you can just beautify, simplify this in this particular expression. So you can say that dou SSE by dou B1 is this, and dou SSE by dou B naught is this. And now we'll take these two and we'll set them equal to 0. So this is the first derivative set equal to 0, and this is the second derivative set equal to 0, right? So these are the two equations. Now we'll simplify this. So minus 2, now we'll do it one by one. Let's focus firstly only on the equation number 1. Okay, so from equation number 1 I'll say simplifying, let's say equation 1, only equation 1 for now. So minus 2, so basically we can just multiply it by minus half on both the sides, so that is gone. And then we'll distribute summation, that is we'll take the summation side inside the bracket. So summation applied on yi minus summation applied on b naught minus summation applied on b1 xi. Okay, now this particular term is basically, this is a constant, right, and this can also be taken on the other side, because ultimately we know that we are deriving for b naught. So we have taken this particular term on the other side over here. Okay, and as you can see it can be simplified further. So this is a constant, so we are basically getting n b naught over here, and we can take the n on the other side, so it will be 1 by n summation 1 to n yi minus 1 by n, b1 is also outside, summation I goes from 1 to n xi. This is basically the definition of mean. This is the definition of mean, right? You take the sum of all the yi values and you divide it by n, so you get the mean value of y, and you take the summation of all the xi values and you divide by n, you get the mean value of x. So mean value of y minus b1 times mean value of x gives you b naught. So we have derived the equation or the closed form formula for b naught. Now next we have to derive the closed form formula for b1, and for that we will use the second equation that we have. Okay, so this is the second equation that we have, that is the dou SSE by dou b1. Okay, this is the second equation, this is equation 2. Okay, so we distribute xi, firstly we multiply all the terms by xi, and then we take the summation inside the bracket. Okay, and then we take all the b1 terms. So again b1 is our target, we know that, so b1 terms will take on one side, so b1 term we have taken on one side, and now here we substitute the value for b naught. This is the value of our b naught that we had got. In fact I am substituting this penultimate step, this particular step I am substituting over here, the penultimate step I am substituting over here. So b naught can be substituted as 1 upon n summation I goes from 1 to n yi minus b1 1 upon n summation I goes from 1 to n xi. This entire thing I substituted over here, and summation I goes from 1 to n xi. Now I can multiply, again I can multiply the summation I goes from 1 to n xi inside this bracket. Okay, inside the green box. So I'll multiply this with summation I goes from 1 to n xi, and I'll multiply this with summation I goes from 1 to n xi, and when I do that I get something like this. Okay, I have multiplied both of them by summation I goes from 1 to n xi, and then this particular b1 term, so I'm gathering all the b1 terms together, so this particular b1 term belongs over here. So that is what I do, I basically take this b1 term together on the left hand side, and we take b1 common, and then we divide the LHS by the and we divide the RHS by the coefficient of b1 in the LHS. So we get this particular expression for b1, the closed form expression. So now, as you can see, we can first calculate b1 simply from the given data of xi and yi, and once you get the b1 value, you can substitute that in this particular equation and you can get the value for b0. Okay, so you can get the slope b1 and then the intercept. Okay, so if I summarize what we did right now, there was an objective function j theta, which in this case was the error function. Then we identified the parameters as b0 and b1. Then we found the partial derivative with respect to b0 and partial derivative with respect to b1 and solved it. So in general, we set the partial derivative with respect to theta. So dou j by dou theta equal to 0, and we solved for theta. Okay, so if you have any questions, any doubts, do post them in the comments below. I hope now you know why you use this particular formulae for finding the coefficients of linear regression. Thanks.